This conference will now be recorded.
Okay, good. Okay, so after this initial delay, I can continue telling you about central limit theorems. And so I haven't had time to write the outline because of these technical problems, but I guess it's going to be okay. So I was talking last time about the central limit theorem and its generalizations. And so what I told you is that when you have power law distributed variables with a tail that I usually write like this, then when mu is greater than 2, it's the usual CLT with all the provisos that we mentioned, that you have to use it in the correct region, and this region might depend on the problem and so on. But when mu is less than 2, then something different happens. And in particular, what happens is that the rescaling is not the same as usual, in the sense that Sn, if you start from, again, even distribution, not to care about the mean, so I'm going to think of a problem where the mean is 0, just for simplicity, then what we saw is that the order of magnitude of Sn being the sum of the xi, is not square root of n, but is n to the 1 over mu. And I ended up last time saying we've encountered this n to the power 1 over mu before. It is actually exactly the same order of magnitude as mn, which is the maximum over all these random variables of xi. And so this means that, in a sense, the sum is dominated by its largest terms, okay? And this is very different from what happens in the usual CLT case, where Sn is over the square root of n, and when mu is greater than 2, square root of n is much larger than n to the power 1 over mu. So I name this situation democratic in the sense that all the variables contribute more or less equally. And here we're in a case where this democracy is fading and a few actors play a major role. So that's what I want to tell you about today, is about something that people call concentration. It's also called localization. And I'll mention that in some physical context, it is also associated with something that people call freezing. Okay, so what I want to talk about now is how to characterize this thing that I said in a hand-waving way, that is that the sum is concentrated in a few of its members, of its constituents. And so I'm going to introduce a concentration indicator which happens to have been introduced in various names in different contexts. So for example, in physics, it's called the inverse participation ratio. And in economics, it's called the Hafindel index. And it still has other names in ecology and other disciplines. But so this idea that I'm going to talk about, you actually is going to be related to something that you know very well. But it is something that has been introduced in many different contexts. So in order to keep the discussion as simple as possible, I'm going to focus on variables that are non-negative. And actually, a lot of my examples later in the lecture are going to be, a lot of my examples are going to be devoted to these positive random variables, like wealth or number of species or number of the population in a city and so on. Okay, so x is a positive variable, and I'm going to associate to xi a weight, wi, which is the weight of xi in the sum. And so wi is by definition xi over Sn. Okay? So because all the xi's are positive, all these weights are also positive or zero. And clearly, by definition, sum over I of wi is 1. So these are really weights. So let me see. Until when can I write? Here you see. Okay, I should stop here. Okay, so now from these weights, I'm going to introduce a family of these concentration indicators. And one special member of this family will be the Half-Interval Index or the inverse participation ratio. But you, in principle, other members of the family can be important too. And one of them, as physicists, you already know about. So I'm going to introduce these Half-Interval Index, curly H index Q. So there's an index Q which parameterizes this family, and it's going to be equal to the sum over I of wi to the Q. And Q is going to be positive or 0. Or actually, very interesting if they're larger or equal to 1. Okay, so the standard half-interval index is Q equal 2. For Q equal 1, then obviously because of the normalization, H is always equal to 1. H1 is always equal to 1. And if Q is equal to 1 plus epsilon, with epsilon going to 0, then by a very simple manipulation of this sum, you see wi to the 1 plus epsilon, I'm going to write as exponent of wi. Well, let me write it down. So if I write wi to the 1 plus epsilon equals wi times exponential of epsilon log wi, then what I find is that HQ is, to first order in epsilon, equal to 1 plus epsilon sum over I of wi log of wi. And most of you, I guess, know that this object here, if you have weights that sum to 1, i.e. probabilities, then this object is minus the entropy of the W's. And again, this, as I'm going to show for the half-interval index, you already see that this is going to be a measure of concentration. We know that entropy measures how the probability over phase space in a thermodynamical system spreads out over all possibilities. If you start from a well-defined initial condition, the probability is localized around this initial condition, and the entropy is small. And then we know, by the way, I need to remove this because starting to lack oxygen. Okay, so we know that entropy is growing with time, and this is associated with the fact that as time goes on, the probability distribution that I'm going to draw in a kind of abstract phase space, starts off localized around an initial condition, and then as time goes on, it spreads out, and it becomes more and more uniform over phase space, at least in the micro-canonical ensemble. And so, indeed, HQ when Q goes to 1 is associated to something that measures how concentrated or how uniform the WIs are. And it's the same for all values of Q greater than 1. And in particular, let me focus on H2, which is the sum over I of WI squared. And so imagine, for example, that the WIs are all equal to 1 over n. So this is complete uniformity and no concentration at all. Then you find that H2 is the sum over n terms that are equal, and they're all equal to 1 over n squared. So it's 1 over n. And this goes to 0 as n goes to infinity. So this indicator, this half-interval index, goes to 0 when the weights are equally distributed. But imagine, on the contrary, that one of the WI0, say, is a fixed number, A, and then all the other ones, WI different from I0, is equal to 1 minus A times 1 over n minus 1. Okay, so in this case, we would have weights that are concentrated around one particular value of I and uniform elsewhere. Then you see that, well, I've actually defined it in such a way that the sum of the WI is equal to 1. But if I compute H2 in this case, and take the limit n to infinity, I find that it's equal to A squared, which does not go to 0 when n goes to infinity. So that's the nice property about H2, or actually other values of Q, is that it's an indicator that for very large systems is either very small if the weights are well spread out, or remains of order 1 if there's concentration. And so I'll speak about concentration in this case. So concentration is when the limit when n goes to infinity of H2 is strictly positive. Okay. So let's go back to the central limit theorem and ask about the values of H2 in the different cases. And so when mu is greater than 2, not surprisingly, because of what I said earlier, that Sn is square root of n, and it's much bigger than any of the random variables, because the largest one is much smaller, is n to the 1 over mu, which is much less than square root of n if mu is greater than 2. Then what you find is that H, and by the way, from now on, I'm going to drop index 2. I'm going to call H the half-interval index. By default, this is Q equal 2. It's of order 1 over n. And it goes to 0 when n goes to infinity. When mu is less than 1, on the other hand, H is of order 1 when n goes to infinity. And so we are in a situation that I call concentrated. And again, intuitively, it's clear that the largest term has a finite weight because it's of the same order of magnitude as the whole sum. And so we will be in a situation a little bit like this. Actually, it's a little more complicated than this, but you understand already from the scaling that we're in a concentrated situation. By the way, there's something interesting to mention here is what do I mean by of the order of in this case? Well, you see that H2 is itself the sum of a very large number of random variables, okay? The WIs are random because the XIs are random. And so here I'm summing many random variables that are all actually less than 1. And so you might naively think that there's some kind of central limit theorem, or at least the law of large number, that applies to this sum. But when mu is less than 1, this is not the case. What happens is that H continues to fluctuate, does not converge to a number. So what I mean by this is that although you sum a very large number of terms, this concentration indicator is always over the 1, but it's going to vary from one sample to the next. So what I call a sample is a particular choice of x1, x2, xn. And for each of these samples, you'll get a different value of h. So it's a strange situation, which often is called non-self-averaging. So one sums a very large number of items, but still never converges to anything. And so if I now plot the distribution of h, since it doesn't converge, it must have a non-trivial distribution. And it indeed has a very funny shape. So h is between 0 and 1. So I failed to mention this, but it's very easy to show that this is between 0 and 1. And the distribution, as I said, a very exotic shape. It diverges close to h equal 1. Then it has a little bump at 1/2. Then another singularity at 1/3, and so on. So it looks like this. The distribution depends on mu, and in particular, the average value of h. So the average value of this distribution is equal to 1 minus mu. Okay, so when mu goes to 1, we leave this extreme concentration regime, and the average value of h goes to 0, and the whole distribution actually moves towards 0. Whereas when mu goes to 0, that is for really extremely broad distributions, the average value of h goes to 1, which means that a single term always dominates the whole sum. Okay, so we have a concentrated situation here, or localized on a few random variables. We have a completely delocalized situation in the usual central limit theorem case. So what happens in the middle? And so you've seen that I've carefully left space for the intermediate case, which happens to be much more subtle in the sense that the typical value of h, I'm going to write it typical, which means, for example, the median value, the value such that there are half of the samples that have an h less than that, and half that have an h greater than that. So the typical value is of order n to the 2, 1 minus mu over mu. Whereas the average value of h is dominated by rare samples and is of order n to the 1 minus mu, which is much greater than h typical. So I'm not going to show these scalings, and if you want to try to do it, I think it's a nice exercise to try to think of how you would show this. For example, how would you show that the typical value of h is of this order of magnitude? This is not terribly complicated with the tools I've given you already. I mean, the hand waving tool, but I think you can do that. It's a little more complicated to show this, but if you're interested, we could discuss of how to plant the problem in such a way that you can actually compute this exactly, including the prefactor. So this is not really concentrated because h goes to 0, but it's not really delocalized either because h is not of order 1 over n. 1 over n means that it's really well spread out over all sites. So there's a kind of pre-concentration effect here, but it's not fully developed, okay? So we'll see an example of this phase transition, as it were, between a delocalized phase and a localized phase in the example I'm going to discuss in a few minutes. But you see that there's an interesting phenomenology coming out here. And I would have loved to show you an example of that, a visual example of that. But unfortunately, well, because we had to change computer, my file is not on the computer anymore. Maybe you have it, yeah, of last time. Can you share the screen? So maybe we can do it thanks to. Oh, okay. If it's too complicated, I'll show you next time. I'll start by that next time. Okay, don't worry. We'll do it next time. So do you have any question at this stage? No, don't worry. We'll do it next time. Okay, so this is a concentration indicator. There are many different ways to characterize inequalities. So you see that inequality is what H measures. So mu greater than 2 means that there's very little inequality. Mu less than 1 that there's huge inequality. And before moving on to the next subject, I want to mention another very popular measure of inequalities, especially in economics, which is called the Gini coefficient. So I'm not going to go into much detail, but just want to give you the definition of the Gini coefficient, which is another natural way of measuring how unequal the xi's are. And it's famously used to characterize inequalities of wealth or of income around the world. So you'll find on Wikipedia, for example, tables of Gini coefficients measuring inequalities in different countries of the world. And the Gini coefficient G is defined as 1 over 2n, sum over all pairs I and j of xi minus xj, absolute value, divided by sum over I of xi. So what you're doing here is, roughly speaking, you're comparing the average distance between two randomly chosen individuals, I mean the wealth of two randomly chosen individuals or their income, to the average, okay? So this is an a-dimensional object, G, as it should be. Of course, H also is an a-dimensional object. Doesn't depend on the currency in which you're measuring wealth, for example, obviously. And it's a number, again, that's between 0 and 1. Oops, I shouldn't go too far here. And so if it's 0, it means that everybody's equal. And if it's 1, it means that one guy is actually dominating the whole sum. So it's really very close in spirit to the Hufindel coefficient, the Hufindel index. It has different properties though, and I won't go more in details, but you can really see the Gini coefficient as another definition that's a member of a bigger family, and in this family there's also the Hufindel index. So I won't go into that, but essentially these are different measures of inequalities that are routinely used. So just to mention that if you look at wealth inequalities around the world, the Gini coefficient is of order 0.7. So for many countries in the world, which is pretty high. And as we know, it has increased over the last decades. You see the maximum value is 1, so 0.7 is already large. It fluctuates, of course, from one country to the next, or it varies from one country to the next. And in the US, for example, it's even larger than that. Okay. So before moving to one specific example of power law random variables and anomalous central limit theorems, I want to mention something very general at this stage, which is that I've given you one example where the central limit theorem is violated, which is the case where variables lose their second moment, okay? So that's one example where obviously the central limit theorem has to be amended. But what's surprising is that actually the central limit theorem is extremely robust. So I told you at the beginning last week when I started presenting the central limit theorem that usually it is proven under the assumption that you have RID random variables. So independent, identically distributed. But you can add quite an amount of correlations, for example, between these variables, or you can make them non-identically distributed. And in many cases, you're not able to break the central limit theorem. You're only able to break the central limit theorem in some kind of extreme cases. One of these extreme cases is the one I just discussed, the one where you lose the second moment. It's pretty extreme, but it happens. And other cases are, for example, when the xi's that you sum have very long range correlations. Okay, so if the correlation between the xi's, so imagine that the xi's are drawn one after the other, if there's a small autocorrelation in time of these random variables, then as I said, you're not going to break the central limit theorem, it's still going to be Gaussian. But if there's long range correlations, if these correlations decay very slowly, actually as a power law of time, then in some cases, you also break the central limit theorem. So if you want, there are two broad mechanisms for breaking the central limit theorem. One is anomalously large fat tails, and the other one is very long range correlations. And in these cases, you have to do something different. Okay. So let me now move to the main subject of today, which is multiplicative growth. Yes?
So Christian is asking, can someone explain P of H as a function of H, the distribution of the index?
Here you both
Sorry.
Can one derive this form? Okay, so actually, there's no analytical form for this P of H. I'm just drawing it so you can, of course, compute it numerically. What you can do is to characterize the singularity. So there's a divergence here close to mu equal 1. There's a singularity close to h equal 1. There's a singularity close to h equal 1/2. There's another singularity close to all these simple fractions, 1/3, 1/4, and so on. And one can characterize the strength of these singularities, but the full function, you see, it's such a strange object that there's no closed form formulas. By the way, these fractions here, 1, 1/2, 1/3, 1/4, and so on, they have a special interpretation. So in the sense that if you have exactly small n objects that have a weight wi equal 1/n, and all the other ones have a weight 0, then in this case, you find that h is equal to 1/n. Okay? So if you break the sum into equal pieces, there's something singular happening. That's the interpretation of these singularities. You happen to have a kind of special probability for having an exact breakdown in equal parts. Okay, but of course there's no more than that you can say about this function. Okay, so the topic of today, really, in the kind of second chapter of the lecture, is random multiplicative growth. By the way, my screen is inverted, but I guess that you see the, okay, good. Because in my screen, I see from right to left. Okay, so what's the motivation here? So I give you a long introduction about power laws, power law distributions, this exponent mu that I keep calling mu, and they seem to pop up in many different situations. And one would like to understand where do they come from? What do they tell us about the underlying system? And if you have power laws, well, very often they're associated to a phase transition. They're associated to something really very non-trivial happening in the system, where the system kind of hesitates between two macro states. If you think of magnets, for example, then you know that there's a high temperature phase where there's no magnetization, and the low temperature phase where there's some magnetization. And right at the critical point, where the system kind of doesn't know where to go, then you have all these very interesting phenomenon of scale invariance and associated power laws. You remember last time I gave you the link between power laws and scale invariance. But it's not always the case. In some cases, power laws can arise through simpler mechanisms. And one of these mechanisms that I'm going to explain today, before moving to these phase transition examples later in the lecture, is random multiplicative growth. And you'll see that this is a basic setting framework that allows already to cover many interesting phenomena, like population growth, wealth growth, stock market growth, and so on. And so I'm going to tell you about this model in more detail now. By the way, I guess that you received the first chapter of the lecture notes. As I mentioned, this is in preliminary state. I'm rushing to have as many chapters written, but don't think that it's going to be all nice and ready before the end of this particular school year. There's a lot of typos and problems in these notes, I'm sure. So please give feedback if you can. But I just wanted to point out something that I didn't say yet, is that I'm trying to break these chapters into parts that I consider to be less important and parts that are more important. And the less important parts, more technical parts, there's a gray bar on the left. So you don't need to read everything that I've written in these notes. There's a mixture of more advanced stuff and more elementary stuff, and so you can choose between the two using the code bar. I mean the code left bar. Okay, so what am I going to try to describe here? Let me state the problem in terms of city growth. As I told you, cities have a very broad distribution. It has in terms of their size. It's a zip floor. It's one of the oldest examples of a power law distribution, which means that there are big cities and much smaller cities. And so I'm going to call I the index of a city. There are capital N cities in the country. And I'm going to call Zi the total population in city I. Okay? And I'm going to try to model the evolution of Zi in time. And the way I'm going to model it is to postulate that the evolution of Zi as a function of time, dZi dt, is a term proportional to Zi, and I'm going to call Mi Zi. So this is proportional growth. The more individuals you have in a city, the more likely they are to have kids, and therefore the faster the growth of the population. And so Mi is the average reproduction rate. Okay. But I'm going to also try to model the fact that in some circumstances, because the population is more wealthy or less wealthy, or because there are special situations, meaning that newborns have a lower probability of surviving or higher probability of surviving. So this can be due to climate changes or viruses or whatever. So I'm going to add some randomness here. So what I'm going to say is that overall in the city, there's a random term that I'm going to call eta I of t times Zi, which means that even if on average over time the reproduction rate is Mi, there are fluctuations in this reproduction rate, which, as I said, can depend on many different factors. And I'm throwing all these factors into a random term that I'm calling eta I. There's actually another term here that I should write that I'm going to discuss in great length in the next lectures. And so I'm putting it here just to remember it and not completely sweep it under the rug. But there's actually a term that comes from the fact that even if the average reproduction rate is fixed, then from one year to the next, maybe people randomly have more children or less children. And so there's a term proportional to square root of zi times another random variable psi. But I'm just, flashing it, and I'll explain much better where this term comes from later on. I'm going to completely neglect this term for the present discussion. And one of the reasons to do that is that when z is large, square root of z is much less than z, and so I can safely neglect that term. Why am I interested in large z's? Well, because one of the reasons is that I'm going to be interested in the tails of the distributions, and then by definition, the tails are when z is large. Okay. So that's the model I'm going to consider. Of course, I need to specify what this random term here is, and this is going to take a little bit of our time because there's subtlety in the description of this eta I. But before doing this, I want to insist on the fact that I've spoken about cities and population, but you can think of this model in many different other contexts. So for example, you can think of I being an individual, and Zi as its wealth. Okay. In this case, MI would be the average return on the wealth of individual I. And so, I don't know, some smart people may have a larger M and vice versa. And then, also obviously, depending on what the stock market is doing, for example, or the state of the economy, even if you have an average rate of return on your capital, then you expect to also have some fluctuations. Some years are good, some years are bad, and that's what the random term tries to capture. You can think of I as species, different species in an ecological system, and Z as the population of that species, the number of individuals of that particular type. And so again, instead of countries, I have species, and I have the same logic for writing down such an equation. And so on and so forth. So this model can represent many different situations. Okay, but mostly I'm going to tell you the story either in terms of cities or in terms of wealth, but you can adapt the language to any problem that you want to speak about. Okay, so now I need to spend some time on this eta I of t because immediately something is going to pop up, which is how do I solve this differential equation which contains a random term. So I'm going to assume that eta are random, and the time dependence of this randomness is such that, so the brackets mean average value over the realization of the process at different times. This correlation function, so this is the correlation function of the noise eta. Sorry, I should have said something right away, which is that I'm assuming that this has a zero mean. The average value of eta is 0. Clearly, I've put everything in the mean here, mi, so the residual is something that has 0 mean. So this is the correlation function of the noise, and I'm going to assume that it has this shape, sigma squared over 2 tau c, exponential of minus t prime over tau c. So if I plot this correlation function as a function of the difference t minus t prime, then it starts at some value and it decays exponentially over a time scale that is tau c. So tau c is the correlation time of the noise, And if you look at time 0, then time 0 is t minus t prime equals 0, I mean lag 0. That should be a lag between t and t prime. At lag 0, this is 0, so it's sigma squared over 2 tau c. And what is this value at lag 0? Well, it's simply the variance of the noise. Okay, so this is the variance. So this form here means that you have a random process that's autocorrelated in time, but it quickly loses its memory, and after tau c, it essentially doesn't remember what it did in the past. So coming back to my example of populations, you can think, for example, of health situations or crops or whatever giving rise to these fluctuations in reproduction rate. And so if the health situation deteriorates for some years and then improves again for some years, tau c will be of older years. And it's not necessarily true that it's going to be exactly of that form, but that's the way I want to think about this noise. Okay. So now I want to give you a little story about this random differential equations that depends on what you choose tau c to be. So often in physics, we think of the nature to be not to have any infinitely short correlation time. We always think that there is some cutoff in any phenomenon that you might reasonably consider. So usually in physics papers, tau c is often considered to be finite. It may be small, but it's not 0. It's not infinitely small. And so if tau c is greater than 0, then eta is a random function, but it's a regular random function. So if I plot as a function of t a certain realization of eta, it's going to look messy, it's going to look random, but it's smooth. And I'm trying to, on my plot here, make obvious that this is tau c, okay? And if I have a random function that is smooth, I can treat the differential equation that I've written up there as a kind of, it's not a kind of, it's an ordinary differential equation. And if it's an ordinary differential equation, I can do what I usually do with differential equations. I can, for example, change variables. So imagine that I introduce u equals log z. Okay, then du dt is d log z dt, which is 1 over z dz dt. And 1 over z dz dt is m plus eta of t. So I'm dropping the I here. Okay, I'm dropping I for now because what I'm going to say does not depend on I. So now I have a very simple differential equation, du dt equals m plus eta of t, and therefore u of t is u of 0 plus mt plus the integral from 0 to t of eta of t prime dt prime. So I'm going to come back to that later. interpret what I'm finding here. But before doing that, I want to give you another path that you could follow. Which leads to a different differential equation for U. That can be justified in some cases, but what I want to say here is beware, because there's this famous problem between the interpretation of such random differential equation, is that you could think of tau c to be 0 from the start. Actually, more precisely, because there's an infinite time scale, infinitely small time scale dt, what happens if tau c is of order dt itself? Well, in this case, you see that because the variance of eta is of order 1 over tau c, it means that eta squared is 1 over dt. And so eta is 1 over square root of dt. So if you take the limit where tau c is equal to dt or of order dt and dt goes to 0, you find yourself with a very thick differential equation because eta is everywhere infinite. Okay, so I can't even draw this picture. It's going to be a mess. It's going to be very large, positive, very large, negative, with a 0 correlation time. So what does that mean? So in this case, you have to work hard mathematically and build what's called the theory of stochastic differential equation. So in particular, the big name here is Ito. And the field is stochastic differential equation. And so you can give a meaning to this limit, but in this framework, in this convention, these simple change of variables are no longer allowed, or at least they need to be supplemented by an extra term. So there's a full story to be told about the Ito term and the correction to this change of variable in the Ito convention, but I won't speak about this now. I'm just pointing this out to you, that in some cases you should be careful about what convention is more adapted to your problem. And in many cases, when the correlation time is finite, then there's no problem. You should use what's called the Stratanovich convention. Stratanovich. But in some cases, you should use the Ito convention. So what are these cases? Well, for example, if your model is actually in discrete time, so if time is not a continuous variable to start with, but it's a discrete time variable, and that the noise eta is always posterior to the moment you are now. So you never know what's going to happen in the future. So it's a discrete time step. And every time step, j, there's a new thing that's going to happen in the future and you know nothing about it. So it means that from one time step to the next, there's no correlation whatsoever, and that you're always before the noise, okay? And in this case, it turns out that when you go to the continuum limit of this time step here going to 0, you have to use the Ito convention, okay? So I'll show you later in the lecture a case where it's natural that you must use the Ito convention. Okay, so this was a kind of parenthesis, but it's an important one because here, already I've done something that needs to be justified. This simple change of variable, if you're not careful, then you're going to do something wrong. So there's a huge number of papers in the literature about Ito versus Stratanovich, and when should you use it, and how to avoid making mistakes. I've tried to condense this literature in a few words, and you can have more details, for example, in the lecture notes. Yes, in the lecture notes that the Ecole Polytechnique ones, and Valentina is going to speak much more about this in the TD3. Okay, so let me go back to this result here after having justified where it comes from. Okay, so for simplicity, I'm going to imagine that z at t equals 0 is equal to 1. So u0 is 0. And what I get is that u of t is mt plus the sum of random terms. They're correlated because they have a correlation time tau c. But if t is very large compared to tau c, there's a central limit theorem that holds, even if the variables are correlated. As I told you, the central limit theorem is very robust. So you don't have to specify many things about the états. You know that provided they have a second moment, which we've assumed from the start, then this thing for t much greater than tau c is going to converge to mt plus psi square root of sigma t of sigma squared t, where psi is a normal Gaussian variable. So this is a central limit theorem. Okay. So that's u. I know everything about u. I know that if I shift u by mt, then and divide it by square root of t, then what I get is a Gaussian random variable. And so if I know the distribution of u, pt of u, then I can reconstruct the distribution of z, pt of z. Why? Because it's just a change of variable. So if for all values of u, I know the probability to get a certain u within du, then I know that it's going to be the same number of events that contribute to pt of z within dz. Okay, so I can actually write an equation between the two, which is that all events contributing to u within du are going to be events that contribute to z within dz, with z equal exponential of u. By the way, I'm sloppy in the notations in the sense that these probability distributions, I'm calling them with the same letter, but I like the convention because it's very useful, and I like the convention like the oral convention. That should be read as the probability of u and the probability of z. But of course, t itself is not the same function. Okay, so it's an abuse of notation, but I find it very useful. And usually it's not ambiguous. Okay, so from this general rule, which is true when it's a monotonic relation between z and u. If the relation is not monotonic, it's a little more complicated. But let me drop that for the moment because in this case it's a monotonic relation. Then from this relation, you immediately get that z is distributed according to what's called a log normal distribution. So pt of z is 1 over z, which comes from the Jacobian, the du dz, square root of 2 pi sigma squared t exponential of minus log z minus mt squared divided by 2 sigma squared t. Okay, and this is called a log normal distribution. So it's obvious if u is normal, then z is log normal. There's a log z in the arguments of the Gaussian, and as I said, there's an extra 1 over z which comes from the Jacobian. Okay, so let me say a few things about the log normal, because it is a distribution that is, in a sense, neither fat-tailed nor thin-tailed. It's a kind of a statistical monster. So, of course, this is a description that doesn't mean much, but it was called that way by Benoit Mandelbrot. And the reason he called it a statistical monster is the following. So first of all the moments of a log normal are finite. So if I compute the average value of z to the n for all n larger or equal than zero, then you get a finite result. And this result is exponential of mtn, of nmt, plus n squared sigma squared t over 2. Okay? So this is easy to compute from the distribution itself and a few, one Gaussian integral. So I won't derive it. But what's important to note is that you get a finite result for all n. And if you remember, that's the criterion I use to call the distribution thin-tailed. But it hides under the rug something that is extremely nasty about this distribution, is that although all the moments are finite, you can have a very bad impression about the process if you only focus, for example, on its average value. So usually one thinks of thin-tailed distribution such that if you know about the average value, you know a lot about the distribution. Think of the exponential, for example. So the exponential that I gave you last time, well, you know the average value, and you know that the order of magnitude of all the variables of the exponential distribution are going to be the same as that of the average value. But imagine that m is negative. So I have a log z here, which is u, that becomes more and more negative as t increases, and therefore z itself typically should be exponentially small, right? Okay. So typically u is equal to minus absolute value of m times t. Oops. Okay, I'm sorry, I've written too far and nobody shouted, so someone should stop me. Right. And so typically, z typical is exponential of minus m times t. Okay. So it is true that, for most realization of psi, u becomes linearly small with t, linearly negative with t, that's this equation. And so z typically becomes exponentially small. in T. But if you compute the average value of Z, so not too well organized here, I'm going to erase this. And yeah. So now let's compute average value of Z just by putting n equal 1 in the general equation. And what you find is exponential of minus absolute value of m times t plus sigma squared t over 2. And so what you find is if it's sigma squared over 2 is greater than absolute value of m, then average value of Z increases exponentially with time. So you're in a situation where most probably you're going to observe exponentially small values, but if you compute the average, you're going to find an exponentially large average. So it's a very bizarre situation. And why is it the case? Well, if I plot P of Z as a function of Z for T large, in this case, in this special case, what you're going to see is something that's highly peaked around the typical value of Z. So this is exponential of minus absolute of m t. So this moves, closer and closer to 0. It kind of collapses to 0 at an exponential speed. But there's such a fat tail here that the average value of Z is actually going the other direction. So this is moving in that direction, whereas the red curve, the red line, is moving in that direction. So it's a really weird situation. So although the log normal has all its moments, and although it decays faster than any power law, it looks like a power law in the sense that you can rewrite the log normal distribution. So write it here, log normal in the tails. Then you can rewrite mathematically P of Z, Pt of Z, as in the tails, Z going to infinity, 1 over Z to the 1 plus mu of Z, with mu of Z equal, so what I'm writing here is exact, and then I'm going to comment, log Z over 2 sigma squared T minus M over sigma squared. So this is just a rewriting of the log normal in the tail, but to make you realize that it looks like a power law. Why does it look like a power law? It looks like a power law because actually log Z is a very slow function of Z. So for larger intervals, and these intervals become larger when T increases, you have the impression that there's a power law, there's a well-defined power law regime where in log this would look straight, but actually if you go very, very far, you'll recover the fact that it drops faster than a power law, and you'll recover the fact that all the moments are indeed finite. So you can be fooled by log normals because log normals look like power laws, although they are not. And if you want to use a log normal, you should be sure that the description is valid in the whole regime. Otherwise, you may badly estimate this moment. Anyway, so I wanted to point this out that the log normal is already something that's not a broad distribution, but a statistical monster in that sense. Okay. So now let me go back to my problem. I've dropped the index I because what I've said applies for any I, it's the same math. And what I want to explain to you now is that within this model, there is a concentration transition. So as you see, it's a very simple model in the sense that all the cities are growing independently of one another, or all the wealth of the individuals are growing independently of one another. And let me write again in small here the equation that I'm considering, mi zi plus eta I zi. So that's my equation for each I. So this is an equation that evolves independently for each individual or each city, but still there's something interesting that's going to take place. And the object I'm going to consider is curly Z, which is defined as the sum from I equal 1 to n of these capital Z I. So what is the interpretation of curly Z? Well, it's simply the total population of the country, assuming that everybody lives in a city, or it's the total wealth of the population, or if you have other examples in mind, then it's whatever other example. Yes, you see all my screen, all my board. Okay, so what is going to happen to this object here? It's a sum of random variables because the zi's are random through the randomness of the eta. And furthermore, the z's are independent because, okay, I haven't, this is an extra assumption. I'm assuming that the eta i's are independent from I to j. So there are no correlation between different cities, which may not be true, but that's the model I'm considering. So you have completely independent random variables, and I'm summing them. So what can happen? I'm really in the context of the central limit theorem here. But am I in the central limit theorem, the classical case or the Levy case? Well, let's see. So in order to make the discussion slightly simpler to start with, I'm going to assume that all the MIs are the same, which makes the story even more interesting because in this case, everybody on average grows at the same speed. And so I can rewrite this as exponential of mt, sum from I equal 1 to n of exponential of sigma square root of t times psi. Okay. The psi I here is exactly the same psi as I had here, except that now it has an index because for different cities or different individuals, the realization of the noise is not going to be the same. So the etas are not the same, and so the psi i's are not the same. Okay, so this is the object I have to deal with. And now you're going to understand immediately that something interesting happens by considering two different ways of taking the limits where n goes to infinity and t goes to infinity. So I'm going to consider very large countries and asymptotic times. But I can do this in two different ways. I can first fix t, large, and take n to infinity. In this case, well, nothing can happen, right? Because I've told you that this is a log normal distribution. So it has all its, this random variable is distributed according to log normal distribution, rather. And so all the moments of this random variable are finite. And therefore, I'm in the case of the central limit theorem. So I have CLT. And in particular, the Herfindahl index, that is the weight of a given country in the whole, for the whole country, I expect that H is of order 1 over n. And this is absolutely true. If you take the limit in that way, you fix T large, but you take n to infinity, that's what you're going to find. You're going to find that curly Z is Gaussian, and the Herfindahl index is 1 over n. But there's another limit you could think of, and actually there will be a family of ways of taking the limit that I'm going to go to in a second. You could take the limit in the other way around. You could fix n large and take t to infinity. But if you do that, well, clearly, because t is going to infinity, you're going to pick up from this sum the largest member. Because when t goes to infinity, exponential of sigma square root of t psi max, which is the largest of all the xi's appearing here, is much bigger than exponential of sigma square root of t psi, well, max minus 1, which means the second largest. Okay, because the difference between psi max and psi max minus 1 depends on n. Actually, if you remember, I told you that if psi is Gaussian, this difference actually shrinks with n, but it's anyway fixed, or n fixed. And if I take t extremely large, at one point, the square root of t times psi max will be much larger than square root of t times psi max minus 1, and therefore the exponential is going to be even, the difference of scale will be even enhanced. And so I can drop all the other terms and approximate curly z by its largest term. Okay, so in this limit, clearly it's dominated by the extreme, and the Herfindahl index is equal to 1, or tends to 1. Okay, because as I just said, it's going to be the largest term, which happens to have been favored by past realization of the noise. You see, in principle, all cities grow at the same speed. They have all the same MI, but there's one of them that's been luckier in a way, and it's going to take it all at the end. And so the Herfindahl index tends to 1. So what happens in the middle? Well, I guess that you've already anticipated what I'm going to say, because this is really an illustration of the central limit theorem, the generalized central limit theorem, is that I can take the limit when n and t go to infinity in different fashions. And I've shown you 2 extreme cases. But what I'm going to do now is take n and t go to infinity with a fixed mu, which of course I'm calling u for a reason, which is defined as square root of 2 log n divided by sigma squared t. Okay. So I'm taking the limit, keeping a certain ratio, so to say, between n and t, or rather between log n and t. So if I take both to infinity, but fixing log n over t, then what you find is that there are 3 cases. Either mu is greater than 2, and you have the usual central limit theorem. So mu greater than 2 means for example, fixing t and growing n. So it was the first case here, fixing t, growing n. And at one point, your mu will be greater than 2, and you'll be in the CLT case. But there are the two other cases as well. For mu between 1 and 2, you have the Levy central limit theorem, and the Herfindahl index is, well, what I gave you a few slides ago. So it's n to the 2, 1 minus mu over mu. Sorry, bad writing, but I've written it before. It's exactly the same result. And for mu less than 1, then you have also the Levy central limit theorem for curly z, L mu of curly z. L mu of curly z. And the Herfindahl index is of order 1. And clearly mu less than 1 corresponds to the second extreme case here, where I fix n and increase time. And then, as you see, if I do that, mu is going to get smaller and smaller. And at one point, become less than 1. So this is exactly the same phenomenology as the one I gave you a few blackboards ago. The Herfindahl index is distributed according to this strange wiggly curve. And so here what you see is that you have a kind of phase transition in the sense that if I fix n very large and increase time, and I plot the Herfindahl index, then for a long time, for the time it takes to reach mu equal 1, you will have an Herfindahl index that's very small, okay, that you don't even see. And then from a certain critical point onwards, the Herfindahl index is going to grow linearly and then reach 1. Okay. So if you have independently growing processes, at the beginning, you have a fair amount of equality, of democracy. But as the time goes on, and as randomness becomes more and more prevalent, in the sense that this term becomes more and more relevant, at one point, you will break this democratic aspect, and you'll find that a few members of the sum are going to contribute in an outside fashion. Okay, so it's really what the Herfindahl index tells you, is that you have a localization of the population in some cities, or the wealth in some individuals, and so on and so forth. But what is nice is that this happens in a model where everything is independent. Okay, it's really the natural growth, independent growth of each of these variables that at one point makes the whole thing collapse in a few, in the hands of a few individuals. So let me give you a few more details about all this. So I haven't given TC here, but it's clear what TC is. TC is the value of T such that mu equal 1. So TC is equal to 2 log n over sigma squared. Okay. So by the way, you see that because of the log n here, even if n is very large, even if n is a million, log n is not very large, and therefore TC is not very large. So very quickly you end up concentrated. Okay. So a few remarks. Note 1, the scenario that I've just outlined in detail, for example, the value of mu, relies on the fact that psi is Gaussian. But I put a question mark here because actually you can show that you can have a much broader distribution of psi's and still keep exactly the same phenomenology. So assume that the distribution of psi, which I call rho of psi, decays for psi going to infinity as exponential of minus psi to the s. So if s equal 2 is the Gaussian case, of course. But provided s is strictly positive, so provided it has this kind of exponential tail with some power, then for any s positive, you have the same phenomenology. So the value of mu is a little different, but the fact that you have this succession of phases between central limit theorem, Levy theorem, delocalized, and Levy theorem localized, it holds in a much broader sense than just this example that I gave you where psi is Gaussian. Now the second remark, which is that here I've assumed that all the MIs are equal. So in principle, everybody's treated on the same ground. There's no distinction in terms of intrinsic quality of the city, or you know, if you think of wealth, there's no, you don't believe that some investors are more are smarter than others. They have the same expected rate of growth in these two examples because the MIs are all equal to M. But of course, you could imagine that M itself is random, not in time now. It's fixed in time, but random over individuals. So some have a larger M forever, and others have a smaller M forever. And so if I assume that, for example, MIs are Gaussian with mean M bar and variance sigma, capital sigma squared, okay? I'm assuming that MI is now a random variable fixed in time, but random over individuals, and that the repartition of these M's over different individuals is Gaussian. Then you find again the same phenomenology, but what changes is the value of mu. Mu is now given by square root of 2 log n divided by capital sigma t. And so in particular, the condensation transition, the localization transition, occurs faster. You remember Tc was 2 log n over sigma squared. Now Tc is square root of log n. So it's intuitive. It's due to the fact that in the first case, it was random fluctuations for, you know, a priori equal cities or individuals that led to localization. Now it's the fact that, you know, some individuals, like by assumptions, are growing faster than others, and this will lead to this concentration happening before. But again, you find the same phenomenology. Good. And to finish, so for once I'm on time. To finish, I'm going to give you an example of exactly what I've said up to now in the context of growth, an example coming from physics. And this example is called the random energy model. It was invented by Bernard Derrida in 1980. And it was invented to understand the problem of so-called spin glasses, which I maybe speak about a little more later. But you can think of that as a model to understand the thermodynamics of random objects, of amorphous objects. And so remember that the partition function of a thermodynamical problem, Z, is equal to the sum over all configurations of exponential of minus beta E of C. So this is the so-called partition function. And for those of you who have gone through statistical mechanics courses, you know that beta is the inverse temperature, and the partition function contains all the thermodynamics of the system. For example, the free energy is related to the log of this partition function. But you can also define the weight of configuration C, which is exponential of minus the Boltzmann factor divided by capital Z. And this gives you the probability to be in configuration C. And there's no reason why you shouldn't think of this problem the same way as we thought about what I talked about before. So you can also introduce the Hafindel index. And the Hafindel index will just be the sum over all configurations of W squared of C, okay? And so again, the question will be whether this Hafindel index goes to 0. And if it goes to 0, it means that the system is exploring over time a lot of different configurations. So in a sense, it's a liquid. Okay. But if this Hafindel index, even for large systems, tends to a constant greater than 0, it means that a substantial fraction of the time, the system will be found in only a few configurations. Okay, there's only a handful of configurations that are going to contribute significantly to the partition function. And in this case, you want to call it a glass. It's a glass because the system gets stuck in some configuration and not others. So at this stage, I haven't said anything about the energies of the configuration. And what Derrida proposed is to think of a random system in a highly simplified manner, such that the energy of different configurations are all independent random variables. Okay. So of course, this is an enormous approximation, because if you think of a real glass, if you change a little bit the positions of the molecules, the energy won't change much. So there's no real deep, trivial at least, reason to believe that at some site. But there might be other ways to think about the problem which actually show that Derrida got it right, but that's much beyond what I want to tell you today. The only thing I want to tell you is that as soon as you make this Derrida assumption that the energies are independent random variables, then what you see is that the problem I'm considering here is formally analogous to the problem I consider above. And so, okay, one has to get the scaling right. I've swept under the rug the dependence on the size of the system, of the energies and the number of configurations, which play the role of T and N if you want. But if you formulate the problem in a natural way, what you find is that the Derrida random energy problem model has exactly the same phenomenology as the one I gave above. And in particular, now what plays the role of time is inverse temperature. And so what you find is that there's a critical temperature Tc, which is 1 over beta C, such that if T is greater than Tc, the Half-Indel index goes to 0 with the size of the system. And so the system is indeed a liquid. And if T is less than Tc, then the Half-Indel index, the average Half-Indel index is given by 1 minus mu, you remember? So it's 1 minus T over Tc. And so you get a glass. But if you go into the mathematical details of the model, you realize that it's exactly what I told you up to now. So for free, in a sense, we've solved the random energy model. So of course, here I have not distinguished between mu greater than 2 and mu less than 2. And what happens is that there's an intermediate temperature regime between Tc and 2Tc, where something intermediate happens. The speed at which the Half-Indel index goes to 0 is anomalous. But apart from that, there's nothing much different between the two temperature regimes. So usually one does not distinguish the two and just focus on the glass transition. So Tc is the glass transition. And so you see that from this point of view, the freezing transition is really a transition of condensation in phase space. So that's the idea. Freezing is equal to condensation of the Boltzmann weight in phase space. So although what I told you today seemed very far from physics to start with, in the end, we recover a very interesting example of this condensation transition in the context of solid state physics. So that's what I wanted to tell you today. I hope I was clear and not too fast. Again, it's very, very difficult to know whether you're following what I'm saying. So maybe I can take a few questions now. Hello? Is anyone still there?
Yes, excuse me.
Okay. Any question, any remark, complaint?
Yes, I have a question.
Yes?
Yes, I don't fully understand on the upper board why the criterion for the different phases, the mu, I don't fully understand why its expression comes from with the square root of 2 log n and sigma squared t. Does it come from the power law expression of z?
You're asking where this equation comes from?
Yes.
Yes. Okay. Yes. Well, as I said, I mean, what I'm trying to do is to find a balance between going into too much details over the mathematics and giving you the story. So if you want to derive this thing, what you should do is to use the extreme value statistics. That is something that I've alluded to last time. the distribution of the largest variables. Okay, and if once one knows how the size in the extreme behave, then it's not very complicated to show that the distribution of this object here is a power law, and the exponent of the power law is given by this. So one has to do a little bit of computation, but essentially what happens, and you'll find in the notes, is that for a broad family of distributions, and actually this corresponds to the family I've written here, the tail of the distribution of the maximum events of these ones is exponential. And this exponential tail is independent on the value of S. Okay. And so that's what's interesting is that once you have an exponential distribution for the size in the tails, you have a power law distribution for exponential of psi. And the exponent is given by that. So maybe it's worth me giving you something that will help you thinking about these problems. And I'm not sure, will you speak about this particular case, Valentina? Oh, okay. So you'll have that in a, okay, you have that in a TD, but this is what I call the battle of exponentials. So if you have a random variable x, which is such that it decays as exponential of minus lambda x, but you're looking at y, which is exponential of beta x, okay? So you have variables that have a very, very small probability to be large, but you're looking at the exponential of these variables. Then it's easy to show, and you'll see that with Valentina, that P of y is 1 over y to the 1 plus mu, with mu equals lambda over beta. Okay, so you'll see that in detail, but what I want to say is that this argument is really behind the way you go from this thing to mu. Okay.
Okay.
So you can try to do it if you want, but otherwise I can help you, or Valentina can help you.
Okay, thank you.
Okay. So for those of you who want to leave and make a pause before Valentina starts at 11, I can stay 10 more minutes if you want and interact with you. So I guess you see my screen okay? My blackboard okay, from what I see?
Yes, sorry.
Hello, yes?
Yes, the mu in question is kept constant while you keep increasing n and t up to infinity.
I'm sorry, it's very hard to hear you. Your mic doesn't seem to, you're all muffled.
Yes, maybe, I'm sorry. Is it okay?
Maybe you can type your question then? So the mu is kept constant. Yes, exactly. Exactly. This is the point. This is how, you know, coming back to here, I gave you two extreme cases where you take n and t to infinity, but t fixed very large, n going to infinity, and the other case here. And I said there's an intermediate regime between the two. And of course, the intermediate regime can be parameterized by a lot of different ways. But the correct way to parameterize it to get something non-trivial is to introduce this object here and now take both n and t to infinity at this fixed rate, if you want, between the two. And this is the proper, if you want, the mathematical way to actually get to these results. These results hold mathematically in the limit I set. So you need both t and n to be large, but keeping this fixed. But of course, in practice, and that's what I try to allude to here by making this little graph, in practice, you'll never be in that mathematical limit, but you'll be in a limit where n is large and t grows. And if you're in that case, where you can't really take that limit with this fixed, then you have a phase transition as a function of t. But then if everything is finite and not infinite, all these statements become approximate. I mean, they become, and they're not asymptotic, rigorous statements. They're just approximate descriptions of what's going on. Okay. Okay.
I have a question for the random energy model. So you mentioned that first sight seems to be a naive model. Then you said that if you look a bit more closely, it's a good model. Can you maybe give just a little explanation why it would be a good model?
You mean the random energy model?
Yes.
Yes. Okay. So the idea that makes it a good model in the end is far from trivial, actually. And it came in a sense as a surprise, in the sense that you can write models which have a microscopic formulation in terms of spins, if you want. So these are real degrees of freedom with a real Hamiltonian coupling these spins. And then you make a complicated calculation, and what you end up with is something that has exactly the phenomenology that I've just given to you. So in a sense, the microscopic model you started from appears to map exactly onto the random energy model in some limit, in a way of thinking about it. And so the reason is that although individual configurations cannot be considered as random, and so this is a very bad approximation as independent, what happens is that if you group configurations together and make bundles of configurations, then these bundles of configurations can be considered as independent. So let me make a little drawing of the landscape of the energy of these random systems. So of course it's a very bad drawing, because configuration space is a kind of infinite dimensional object, and I'm drawing a one-dimensional function. So you know it's a very, very bad picture of what's going on in infinite dimensional spaces. But what, you know, in words, what happens is that the energy of this configuration and of this configuration, they can't be considered to be independent. They're very close by, and so it's stupid to think that they're independent energies. But what happens physically is that the system is going to be stuck in this valley here. So this blob of configuration holds the system for a certain time, and so there's kind of local equilibration within the valleys. And now if you coarse grain the system at the scale of the valleys and think not of the individual energies, the configuration of individual, the individual configuration energies, but rather the free energy of these blobs, then it's a much better approximation to think that these are independent random variables. And then what I told you, the note 1 that I erased, is that it doesn't depend much what the tail of the distribution of these energies is really, because in the end, it's all going to map to the same model. And this is due to the universality of the statistics of extremes, if you want. So any distribution that falls as exponential of minus psi to the s, if you want, is going to be in the same universality class. So there's a conspiration of many subtle points here that in the end make the random energy model not such a bad model after all. And I haven't given you some of the properties of the random energy model, some of the thermodynamical properties. But as a kind of bare bone model for glasses, it's surprisingly good in view of the information that you've put in the model, which is close to zero. Okay, so that's the story in a nutshell.
Thank you.
Okay, I think it's time for me to leave the floor to Valentina. I'm going to erase my board and say, yeah, sure. And you need this. Okay, see you next week.
This conference will now be recorded.
Very good. And can you see the blackboard? Because maybe using this color, which is lighter, is not great, right?
It's okay.
Okay, great. Okay, so welcome everybody to the first day. As I told you several times, my name is Valentina, and this is the email where you can find me for any questions or comments or whatever you want to tell me. So there are several things that I wanted to mention before we start this today. So the first one is about the mailing list. So you should have received an email either on Wednesday evening or during the weekend stating that you are included in the mailing list and with some information about the course in the today. So in case you have not received this email, please either write your email address on the chat or send me an email so that I can add you to the list. And this is important because we will send information about the course in the today using that mailing list without going through the mailing list of the full, the same master course. And the second thing that I promised to discuss with you today is about the duration of the TEDs. And the fact is that we have 1 hour in principle, so the TED should be from 11 to 12. But there are some TEDs which are a little bit longer, and we saw last year that this time was not enough to discuss, let's say, all of the exercises. So for this reason, this year, well, first of all, I'm giving to you the text of the TED in advance. And the idea is not that you solve the exercises before we discuss them, but it is more that you look at the text. So there will be in future TEDs some problems or exercises which are formulated in a language that is a little bit different. So one has to familiarize a bit. So there's somebody who doesn't hear. Is it a problem? Yes means that you hear me, right? Yes, okay. Okay. So sorry about the problem, and in case, feel free to speak, so that I can see these more directly than on the chat. So as I was saying, the idea is that maybe it would be good if you look just at the text of the today a bit in advance, so that we spend less time during this hour to discuss the framework. And on top of that, what we can do is to make the study session a little bit longer. So let's say until 12:15 or 12:30. But this depends on you. So there might be people that have courses after this. There might be people that have constraints. There might be people that find it very tiring to stay online all of the time. So so what I thought about doing is a little survey that we can do maybe at the end of this study. So I will give you a link to our website, and you just have to click whether you would prefer to have it 1 hour long or 1 hour and a half, and then based on the average, we can decide that, unless there is somebody who tells me that there are sharp constraints and that we do have to finish at 12 because you have maybe other courses afterwards. So if that is the case, let me know now. Otherwise, we do this little survey at the end. Okay, so what is the plan of the day of today? So this one is going to be actually a little bit shorter, I think, because it might be about things that everybody here has seen at least once in her or his life, in the sense that what we are going to do today is discuss some basic stuff about probability, in particular this formula of change of variables that have been that popped out in the lecture also today. And we are doing this with a perspective that is the one of power laws, since this has been discussed a lot in the last lecture and in this lecture. So the idea is to try to see how these power laws emerge and what are possible mechanisms to get this type of distributions. And just to give an idea of the first 3 days, this will be more generally about probability, like today, a little bit of statistics in the next day. So the next one will be about maximum likelihood, and there will be also statistics and the Kolmogorov-Smirnov test in particular in the last day, the number 9. And then the third day is about stuff that has been introduced today. So Ito versus Stratonovich and Langevin, and in general stochastic calculus. So this is a pretty long today, but we will go back to these issues when discussing a particular example in today 7. So that's a bit the plan for the first 3 weeks. And now let me start with the problem of today. So I think, and I hope you all have the text of the today, which was in the ENS folder. But just in case, so let me recap very fast what is the theory that is behind all of the exercises. So the idea is as following. We have some random variable that I call capital X. That takes values, let's say, in R. So you have a density function for this random variable that I call rho of X. And in here, in this today, I'm using this subscript to indicate what is the random variable of which I am computing the density function. And of course, what's in parentheses is the value that I assign to the function. So this is the density. And let me also introduce the so-called cumulative density function, which is what tells you what is the probability that your random variable takes values which are, let's say, smaller or equal to this small x in here. So you get it integrating from, let's say, -infinity or whatever is the lower edge of the support of your distribution up to the point x, your density function evaluated at y. So this is a cumulative density function. And now the problem of today is the following. We have a new random variable y that is related to x through some functional relation, so through some function g. And we want to understand what is the distribution of y, given that we know the distribution of x. And there is a simple formula that was written also today in the lecture before at the blackboard, which assumes that g is monotonic. And this formula tells you that you get the distribution of y simply taking the density of your original variable x and dividing it by the absolute value of the derivative of the function that gives you the relation between these two random variables here. And what you have to do is to compute this at x, which is the inverse through your functional relation of the point y of which you want to compute the density. So this is the very basic formula that is more or less everything we will need for the exercises of today. Okay, so let me give you a little trick to remember this. So of course, one way to remember this is to remember what is the formula for the change of variables of the delta function that you can use to relate the two random variables. But here, let me give you another trick, which is more, let's say, probabilistic in flavor. And the idea is to derive this using this cumulative density function. So suppose that we have a function g. So this is my x. This is g of x. And we have a function which is monotonic. And I take it to be increasing, for example. And I want to compute. So I fix one value of y, which corresponds to one and only one value of x, because the function is monotonic. And what I want to do is to compute what is the probability that my random variable x is smaller or equal to some given value of x. And because you have this one-to-one relationship, you see that you can write this. So this is nothing but the f of x, which I just introduced. And what you can do is to write it. Asking that x is smaller than this particular value corresponds, because of this one-to-one relationship, to having y, which is smaller than this particular value, which is nothing but the function g evaluated at x. So what this means is that this probability here is exactly equal to the probability that y is smaller or equal to this particular value, which is g of x. And once you have this basic relationship, of course, in here, I'm assuming that g is an increasing function. If g was decreasing, what it would have had instead of this p would be 1 minus this probability, right? Because the relationship is inverted. But once you have this, it is very easy to get out this formula. The only thing that you have to do is to take the derivative of these expressions, because this probability in here is now the cumulative density function of your variable y evaluated at g of x. And now if you take the derivative of the cumulative, what you get out of it is just the density of your random variables. And so taking the derivative of this expression, you would get that rho x of x is what? Is the derivative of this evaluated at g of x. So this is the density of y evaluated at g of x times the derivative of the argument, which is exactly g prime of x. And so you see that you have to bring this on the other side. You replace g of x with y, and then x will be given by g to the minus 1 of y. And this is how you get this formula in here. Okay, so this is simple. Let me just tell you about two generalizations before we go to the exercises. And of course, feel free to ask questions or make comments. You can unmute you. I think that's faster. Okay, so generalization. So the first one is, of course, whenever you have a function, so as you see here, I assumed that the function is monotonic, so either increasing or decreasing, but you may have functional relationships G, which are non-monotonic. And what you have to do in this case to get this rho of y is to sum over all of the possible values of x, which correspond to the particular value of y that you have chosen. So your density will be now given by a sum over all points xi such that g at xi is equal to your particular value of y of exactly the same thing that you see up there. So rho x evaluated at xi divided by g prime evaluated at xi. And if you want to check this expression, you may use, so I will not do the example in here maybe to save a little bit of time, but you may use, for instance, simple example like the function x squared, and you will see that using the trick of the cumulative density functions, you get exactly this formula in here. Stop me if you want me to do this exercise. Of course, we can do it. And the second generalization is if you are in higher dimensions. So you may want to transform variables which are not one number, but which are vectors, for instance. So let's say that x has n components, and from x you want to define some other vector y, such that each component is a function of all of the components of the vector x. So we'll have g1, g2, up to gn of x. And now if you go higher dimensional, what you have to do to adapt this formula in here is to replace the absolute value of the derivative that you had in there with the absolute value of the determinant of a matrix. And this matrix is the so-called Jacobian of the change of variables. So the matrix J has components ij that are what? So this will be the derivative of the if component of your vector y over the jth component of your original random variable x. And if you want to practice with this, there is the bonus exercise of the TD, which is exactly an example of how to use this formula. Okay, so given this, so you will see that there is then a simple example which is solved in the text, which is about this log normal distribution that had just been discussed in the lecture. So I will not go through that again, and I will jump then to the first exercise that is about how to practice with this equation here and how to understand simple mechanisms by which power law distributions appear. Any question? No. Okay, so let's go to exercise 1. So exercise 1 starts like this. You're given a random variable x, which has a uniform distribution, let's say between minus 0 and 1. So the density of my random variable x, I can write it as theta of x. So this is a function which is which takes value 1 only when the argument is larger or equal to 0. And then I have theta of 1 minus x, which tells me that my variable has to be smaller than 1. And the first thing that you're given is a variable y, which is minus lambda log of x with lambda positive. And we have to compute what is the distribution of y. So here you see you have a functional relation between x and y. You have a g of x, which is monotonic. It's just minus lambda log of x. So we just have to apply the formula that I gave before and do a little bit of algebra. So from here we have that g prime of x is minus lambda over x. If we invert this relation, so if we put this equal to y and we invert it, we get that x is equal to e to the minus y over lambda. And given this, what we can say is that is then that rho y of y is what? It's rho of x, so theta of x, theta of 1 minus x, divided by the absolute value of this first derivative. So lambda is positive, so I just have a factor of lambda in here. And then in the numerator, yes, I would have absolute value of x, but because I have this theta, I can just put an x in here, and I have to compute it at e to the minus y over lambda. So what I get out of this is a factor of e to the minus y over lambda divided by lambda. And then you see, so this theta is asking that my exponential is positive, and this is true for every value of y, whereas this theta is asking that this exponential is smaller than 1, and in order to have this, I have to impose that y is positive. So what I obtain is an exponential or Laplace distribution. I see a question. Okay, the left. Okay, maybe I'll try to write a little bit more in the center. Okay, so the logarithm of a uniform distribution is an exponential distribution. And now let me go to the second point. Okay. And let me try to use all the blackboard this time. So the second point is, okay, now you're given another random variable z, which is e to the beta times this variable y, of which we had just computed the distribution. And I didn't write it on the text, but I assumed here that beta is larger than 0. And so now how is this z distributed? Well, you know it from the last 5 minutes of the lecture. What you find is that this is, okay, let me do this. Maybe it's faster. So what is g of y now is e to the beta y. So g prime of y is beta e to the beta y. And what is y is log of z over beta. So using this, the density of our random variable z will be what? So you use the same formula as before, and what you should find is that we can write this density as mu theta of z minus 1 divided by z as the 1 plus mu, where mu in this example is given by 1 over beta lambda. So you have a factor of lambda which comes from the exponential distribution of your variable y, and then you have a factor of beta which comes from this functional relation. So in the lecture, this formula was given, except that lambda was replaced by 1 over lambda, but it is exactly the same thing. So this is a Pareto or power law distribution. And the mechanism is what we said before. So we have a random variable whose distribution is suppressed exponentially. So it is exponentially unlikely to find very large values of this variable y. But what you do in here is to enhance these values of y exponentially through this relation. So you see that this is like the partition function of this random energy model, and this is the inverse temperature. So y would be the energy that here we are taking exponentially distributed. And if you do this combination of exponentials, so the exponential of a variable which is exponentially distributed, what you get out is precisely a power law distribution with an exponent that depends on the properties of both your original exponential distribution. And how does it depend on lambda? Well, the idea is that you see when mu is smaller, the tails of your distribution are enhanced. So you have a larger probability to get large values of your random variable z. And this happens when mu is smaller, which means that either beta or lambda are large. And this makes sense because if you increase lambda, what you're doing through your exponential distribution is giving more weight or more probability to variables or values of y which are larger. So it makes sense that you get a larger value of z. And at the same time, if you also increase beta, what you're doing is giving more weight to these large random variables. So again, it makes sense that these two couplings enter in your exponent through this relationship. Okay, so there is another comment that we can do or make starting from this, which is essentially related to point 3. And the comment is that, so what is this z? Is e to the beta y, but y, we derived its distribution, assuming that y is given by minus lambda log of x, and x is uniformly distributed. So we can also write z as e to the minus beta lambda log of x. So this is 1 over x to the power of beta lambda. So another way to interpret the emergence of this power law is to say that we are given a distribution that is uniform, so which has some flat density, for instance, around 0. And then we take the reciprocal or a negative power of this distribution, and what we get out is a power law of distribution that gives a big weight to values which are large. And this is because we have a finite weight in our original distribution for values which are small, because our distribution was flat and uniform around 0. And so this observation is essentially the idea of, we can make it more general, and this is the idea of the point 3. So the point 3 says, suppose that you have a random variable x whose distribution, rho of x evaluated at x, is, let's say, positive when evaluated at 0. And we also assume that, that this function rho of x is somehow smooth around 0, so we can have a Taylor expansion. So this means that my distribution will look something like this around x equal to 0. And then we can ask, what is the distribution of any negative power of my variable x? So let me introduce y now as x to the minus gamma. And let's use again, so let's practice again with this formula of change of variables. So this is my g. So now g prime of x is minus gamma x to the minus 1 minus gamma. And what is x as a function of y? Well, x is y to the minus 1 over gamma. Okay. So what will be our density? I hope you can see it. Our density of our new variable y. So this will be our rho x evaluated at x, where x is now 1 over y to the 1 over gamma. And then you have this g prime. So gamma, let's assume that gamma is positive. So the absolute value gives me gamma. And then I would have, what I get in here is a factor of y to the 1 plus gamma divided by gamma. Okay. And so what you see is that when y becomes large, so if you look somehow at the tails of your distribution, 1 over y goes close to 0, so we can approximate this density to the value that it has in 0. We can do a Taylor expansion if you want and keep only the first coefficient in the expansion, which we assumed to be different from 0. So this will be rho of x evaluated at 0. And then we have below gamma y to the 1 plus 1 over gamma. So this at large values of y will look like a Pareto distribution with mu equals to 1 over gamma, plus corrections which come from the higher order expansion of your distribution of the variable x. And this is in line with what we found for this particular shape of the distribution. Okay, so to summarize, we have two mechanisms to easily produce power law distribution. One is this combination of exponentials that we will discuss also a little bit more in the second TD. And the other one is to take some negative power or the reciprocal of a distribution which is flat around 0. Okay, so having practiced a little bit with this formula, let me now go to the second exercise, which is an exercise that is a little bit related to the homework. So let me keep this. I don't know if you had time to have a look at the homeworks. And by the way, if there are any problems with setting up the Python or Jupyter, just let me know. We can discuss it at the end of the session. So I will keep this and I will rewrite our change of variable. No, okay. Well, yes, let me rewrite it. Just as a reminder, our formula of change of variables. Okay, and let me go to this exercise 2. So the idea of the homework, for those who had no time to look at it, was to discuss a little bit with real data the emergence of the so-called zip law, which is something that is very robustly emerges anytime you look at distributions in the size of cities, for example, or distributions in the frequency of words, which is the example that we discussed in the homework. And the idea is the following. So you have a text in the homework. I took the example of the book by James Joyce, Ulysses, or Ulysses. And what you can do is to sample, to take all of the words which appear in the text and to order them as a function of their frequency of appearance in the text. And so in this way, what you do is you associate to each word a rank that goes from 1 to the total number of words that you find. So the most frequent word, the one which appears more often in the text, will have rank equal to 1. And what you plot in here is the frequency of the word as a function of the rank. So this is the number of times the word appears. And you can normalize it by the total number of words in your text. And what you find is that, of course, this is a decreasing function because this is the definition of the rank. So the word of rank 1, which in Ulysses is, I think, the word the, is the one which appears with a higher frequency. And then you will have the second most frequent word, the third one, and so on. And what you find several times in this type of real data is that the distribution follows somehow a power law. So you see that f of r goes like 1 over r to some power alpha, and the exponent is very close to 1. And this is what is called zip flow. So this tells you that the most frequent word appears twice as often as the second most frequent word, and so on and so forth. So the idea of the second part of the homework and of this exercise is to try to give a little simple probabilistic model for this type of power law. And this is done introducing a model of random language. So in this random language, what you do is, this is the problem of a monkey with a typewriter. This is how it is called. So the idea is that you have somebody who types randomly on a keyboard, and it creates a text. And the keyboard has a space, and it has a certain number of letters, which I call M in the exercise. And you have a certain probability to hit the space. So let's say the space is heated with a probability that I call Q. Okay, let me write it as prob of heating the space is equal to Q. And then the letters you can hit them with equal probability randomly. So the probability of each letter will be 1 minus q divided by the total number of letters that you have, which is given by m. And what is a word? So in this way, if you type randomly, you will create strings of letters plus spaces, and we identify words that I will call omega with an index I, and I goes from 1 to infinity. So the words are strings of letters plus a space at the end, which tells me that the word is over. Okay, so what we want to understand is what should we expect if we did a plot like this for this example of random language. And let's do this following the exercise. So there is a first question, which is about probability of getting some particular words. So this is point 1. Based on this model. So the idea is that we can ask, now we select one particular word, omega I, which could be, for example, I don't know, A, C, D, F. Here the word has a length which is equal to 4. And I can ask what is the probability to observe in my random text this particular word, omega I. And this probability, you can compute it easily. So now let's assume that the length of the word is small l. What you find is that the probability does not depend on the particular word that you're looking at, but only on the length, so on the number of letters which you have, because letters are all equiprobable. So this is given by q, which is the probability to have the space at the end, times the probability to have 4 letters, which is 1 minus q divided by m to the power of the number of letters, that is the length of the word. Okay, so this gives you the probability of having one particular word of length L. So let me put a small l in here, indicating that you have a dependence on this variable. And once you have this, you can ask, well, what is the probability that I encounter any word of length L? So no matter what is the particular choice of the letter, I can ask how many times should I find words which have length equal to 4 in my random text. And this is again easily derived from this, because what you have to do is to multiply the probability of a word of length L times the number of words that you can create of length L. And how many are these words? Well, for each positioning here, you can choose any letter out of the n ones that you have in your keyboard. And so this probability of length will be m to the L, which is the number of words of length L, times the probability of one of them. And so you see that this, if I interpret length as a random variable, I have something which is exponentially distributed. So this is q e to the L log of 1 minus q, where my lambda in the notation of before is now equal to minus 1 over log of 1 minus q. Okay, so I hope this is clear. And you can check that this is well normalized. So if you sum over all possible values of L, you get that this probability is equal to 1. Okay, now we have the probability of length. And the next thing that we want to try to do is to somehow understand what is the behavior of the rank. And to do this, we want to derive a relationship between the rank that we should expect for our random words and their length, of which we know the distribution in here. And what happens, and this is something that if you did the exercise in the homework, you may have observed, is that in this type of random language, if you try to redo a plot like this, you find something that is apparently a little bit funny. So you find some degeneracies in the frequency of words. So you find that you have a set of words that has more or less the same frequency, which are the most frequent. Then you have another bunch of words which have more or less the same frequency, smaller than the first one, and so on and so forth. And of course, what we want to do is to derive, let's say, the continuous or an interpolation for this data arranged in this way. So why do we have this degeneracy? Well, this comes from the fact that all of these words of the same length are equiprobable. So you have essentially the same probability to find the word the and the word ABC in this type of random text. And this is what gives you frequencies that are very similar. And what you then expect is that all of these groups are distinguished by the length of the words that belong to the group. And so the idea is that words which have length, let's say, equal to 1, so a single letter, they are much more probable than longer words because the distribution is exponential. So they will occupy the first values of the rank because they will appear more frequently. So they will have values of the rank which belong to the interval 1 up to the total number of words of length L equal to 1 that is simply given by M. So stop me here if this reasoning is not clear. But if you understood it, then it's very easy to then identify that the second set of words will have length 2, and the rank will go from M plus 1 to M plus M squared, which is the number of the total number of words of length 2, and so on and so forth. So using this reasoning, we can now ask what is the rank of a word of, or the interval to which the rank of a word of length L, arbitrary L, belongs to. And let me check time. Okay. So let me call it the rank of a particular word. Let me say omega I of length L. Well, this will belong to some interval which has lower bound that is given by the sum of all of the ranks of the words with shorter length. So this will be sum from k from 1 to L minus 1 of the number of words which I have to allocate to get the rank, which is M to the k for each value of the length. And in here, I will have to place, so I have the same thing, but I have to place also the words of length equal to the one that I'm looking at. So this will be something like this. So is this reasoning clear? If this is not clear, please ask questions, or we can discuss this more. But if this is clear, then we can easily do the sums in here. So we get that, therefore, this rank. So these sums we can do explicitly. We get something like M1 minus M1 minus M to the power L. And in here we have the same, except that we have L minus 1 instead of L. And out of this relationship or bound, what we can deduce or what we can set a little bit as an approximation, in the sense that now we assume that somehow the variable R is a continuous variable. We want to functionally relate it to the length L, and these bounds tell us that we can assume that the rank as a function of the length goes like, or let me put an equal here, some constant which depends on M that we are not really interested in, but then we are interested in the dependence on L, and this is of the type e to the L log of M. So essentially the rank goes like M to the L, up to corrections which depend on my constant M. Okay, so this gives us a relationship between the variable of which we know we want to compute the distribution, because this frequency plot is essentially giving us the distribution of the rank interpreted as a random variable, and another random variable, which is the length, of which we know the distribution because we know that this is exponential. And so what we have is precisely this mechanism of combination of exponentials. So let me use the notation that we introduced in the first exercise. So there we had Z, which was e to the beta y, and we had a p of y, which was e to the minus y over lambda. And this was giving us an exponent that is mu equal to 1 over beta lambda for the reasons that we have explained. So what does this correspond to in our example? So y now is played by L, and so instead of lambda, what we have is minus 1 over log of 1 minus q. And instead of beta, there it is. So this is now our new functional relationship, and our beta is what? Is log of n. And therefore, the exponent mu that we should expect for the distribution of the rank is what? Is minus log of 1 minus q divided by log of n, right? And so what this tells us is that in this simple probabilistic example of random language, f of r should go like 1 over r to the 1 minus log of 1 minus q divided by, sorry, I hope you see, log of n. And in front, you have some constant which depends on m and which depends on q. Okay, and now you see that if you make the number of letters sufficiently large, this log of m is large, and therefore you see that the correction to 1, which would be your deep flow, is particularly small, and therefore if your alphabet is sufficiently large, you see that you have the emergence of a power law with the exponent that is very similar to the exponent that you see in the examples with real text. Okay, so this concludes a little bit the idea of the exercise. And there was just one last comment, and maybe we can, if we have 5 minutes, we can look at the homework together. So the last comment is that, of course, this example is very simplified. So real languages are not random languages. And there is one particular, let's say, assumption that we are making, which I think is particularly false for the case of real languages. So can anybody guess what is the thing that perhaps we shouldn't expect if you are dealing with real text?
The fact that letters are equiprobable.
Oh, I don't hear you. The microphone is really bad. Try now. No, I don't hear you anymore. Okay, maybe you can type because it's true. So the fact that letters are equiprobable is more or less exactly related to what I wanted to say, because it's what gives you this factor here. So what we are saying is that any combination of letters is a word, and so the number of words, that we can have increases exponentially with the length. And of course, in real language, this is not true. So it's not true that any arbitrary combination of letters is a word, and therefore it is not obvious that you should expect that the number of distinct words that you have of a given length is satisfies this scaling. And this is something that you will see in the exercise playing with this real data. So now I don't know if we can maybe spend. I'll try to do something. Let me sketch it. Let me just sketch 1 minute and comment on the homework. So on the homework, you will see, first of all, that if you use random language, you do see a zip plot which looks like this. So with all of these degeneracies, but let's say trend that is of the form 1 over r, and this is 0.7, I think, of the homework. And then I also asked at a certain point to plot the histogram of the number of distinct words that you find in your text as a function of the length, and to plot it in log scale. So what you find, so this is, let's say, the length, and this is the number of distinct words in log. And indeed, for random text, what you should find is that you recover, as you should, this exponential behavior, at least for small enough values of L, and then you have that your curve bends. And the reason why it bends is that words with very large lengths are really improbable because the probability decays exponentially. So you have to create texts which are extremely large in order to detect them with their full statistics. So the reason why this distribution bends and you don't see the full linear behavior is that you have a cutoff which is given by the length of the text that you are generating. That does not allow you to somehow sample the tails of this exponential distribution. And if you try to do, so this is for random text. And if you try to redo this for Ulysses, so for real text, you see that this is not quite the case, right? You should get an histogram that goes something like that. Well, not linear, much more curved. This is real text, and this is precisely related to this comment that letters are not equiprobable and not all combinations of letters are making a word in real language. Okay, so that's it. So now I think, so as you see today, the day was short. We are right sitting in 1 hour, but maybe now we can take 2 minutes or some minutes to discuss a little bit about the length and what you would like to do. And so anybody has some opinion, let's say strong opinion about what's best to do? If not, I'll try to make a survey with you. Let me check if this works. So I just want to do a survey online so that we all know the results. If you go to the website that I'm giving you, take the time. Try this. It's the first time I try this system, so I'm not even sure that this works. But I think you should find a window where you just have to choose. Sorry, you're here. Where you just have to choose what you prefer. So we more or less see. And something I should specify is that in any case, I will upload solutions to all of the exercises. So even if we do not have time to discuss everything at the Blackboard, you have the solutions. There is this question and answer file where we can ask and discuss a little bit more if there are things which are not clear. And so even if we choose 1 hour, perhaps there is also a way for you to look at the rest of the material, but 1 hour and a half is a bit better, I think. A bit less frustrating.
Excuse me?
Yes.
Can you just show the upper board, please?
The one which is below?
Yes. Thank you.
Okay, great. Okay, so it seems that there is some preference for making it 1 hour and a half. It's 79% of you. So I think that we can do that. So starting from next time, there are 4 people missing that still have to vote. Okay, I will give you the results, the full results once this is over, but perhaps starting from next time, as you will see that the day will be a little bit longer, the next one and the third one in particular. So maybe it's good to have 1 hour and a half. And then if we go on and we see that there are shorter ones. Of course, we can make everything in 1 hour. Okay, so is there any question? Was everything okay? Any questions also on the homework? I don't know how much time you have to do the homework, but if you have troubles, just let me know now, or we can discuss using the email. And you could read everything, the speed was okay, any comments? Okay, so I take it as a yes. Okay, very well. Thank you, guys. Okay, so yeah, it definitely looks like we can go to 1 hour and a half. So that's what we will try to do next Wednesday. Okay, thanks to everybody. And again, feel free to write in this question and answer files. It does not need to be scientific questions. You can also ask or say comments about the structure of the lectures or problems about exercises, homeworks, and everything. And I will upload right now the solutions to this today and homework and the text for the next today and homework. And we'll see each other next Wednesday. So have a nice week, everybody.
Thank you. Bye.
Thank you.
Thank you. Bye.